thinking that I mean, if you are in a Hilbert space of a complex
In the Hilbert space, you have these two things. You have them. They're just sitting there.
But I'm worried about transposition. Because if you define...
Are you worried about transposition in the Hilbert space?
Yeah.
Yes? Why?
I don't know, because it doesn't need a transpose means just taking a matrix and just putting one side.
Yes, it's a natural operation. It's basis independence natural operation. It's a very innocent thing. It's totally basis independent or choice of your representation of your matrix. It's a natural operation which is sitting there. It doesn't depend on choice of base or anything like that. Neither does complex conjugation of your matrix.
No.
They're just sitting there. They are two components and they prove to be really crucial in everything we do, to have these two factors. That's the difference with Kelly's categories didn't have the transposition, the complex conjugation part. They just have transposition.
I was sort of thinking that if you have a complex Hilbert space and you define the adjoint in a product, you get directly the complex, the conjugate transposition, the complex adjoint.
Yeah.
So
you have them in a Hilbert space.
The complex conjugation is not in the category of complex Hilbert space. It's not something natural. It's something natural.
Ah, but it's naturally. That's the whole thing. That's why Kelly's categories didn't have it.
Okay.
It's just a matter of but in this definition you get it for free. And if you don't, with Kelly's category you can't do nothing which I'm gonna do. You really need this. The problem with, you know what the problem is? That suppose you've got a state, state psi, from I to A. Now I take transposition. This is from A star. This is dual space. Now you can really read this as dual space, dual vector space, from A star to I star. Yes? I cannot compose these two. I cannot make a bracket.
No.
I cannot calculate probabilities.
No.
What I need is to get rid of the stars in a covariant way. And that's what my complex conjugation is for you. So you need this. And this is the essence of understanding Dirac notation. That both there is something about the adjoint there and dependingly how you use it, you will either be using this sort of erasing of the stars or the full adjoint. And it depends where you're using it exactly, whether you're using it in density matrices or something else. So this is like unraveling what is all implicit in the Dirac notation. And you actually use all this when you're doing Dirac calculation. And sometimes you're using one and sometimes you're using the other. So it's really crucial to have them both. And that was missing in much of the mathematics which was existing.
Well, I mean, Kelly may have thought perhaps of vector spaces of an arbitrary field, but now they have only complex conjugation.
The thing is, if you take, but this structure is valid for vector spaces over the real numbers, but just one part is trivial. Like this part, so like there are many categories which are like that, but this part is in many cases trivial. The star will be identity. So I've got a lower star and I've got an upper star. I just use the upper star because it's this transposition is standard in the literature. But there is this other component.
I think we agree much more than you think.
Yes?
Yeah.
Okay. So in many categories, because what is an example of this sort? One example of this sort. This is like a funny one. One example of these categories, which is like very, I showed you, this is not compatible with having any ability to clone and delete, so it's very highly linear. One example of such a category is the category of sets, Cartesian product, and relations. The category of sets, Cartesian product, and relations is extremely close to a category of Hilbert spaces, structurally. It has nothing similar with, say, the category of sets, Cartesian product, and function. It has nothing to do with that.
Because of the adjoint.
The category of relations has these axiomatics. And as I told you, if you've got a terminal object like you've got in set, the thing completely collapses. Yeah. So but why are they the same? Because you can think of varying relation as a matrix calculus in 0 and 1. It's a matrix calculus over the semi-ring 0, 1. So that's why it's very similar. Complex conjugation is completely trivial, of course. It's identity. So relations behave this picture calculus, they satisfy this completely. Although parts of it are trivial. Like this part is trivial for relations. That's So it's highly surprising. Like, this is like the soul of category theory. It doesn't matter whether you take sets and as objects. It doesn't really matter. It's really about this choice of the morphisms, and taking relations instead of functions is such a big deal. Because relations you have the adjoint,
exactly,
the converse relation.
Exactly.
It doesn't exist for functions.
Exactly. Yeah.
So
I think you should, in fairness to Kelly, make clear that what he was trying to do with all this enriched category stuff originally was
vector spaces.
exactly. I mean, he was just starting from closed categories in general, and he wasn't looking at this motivation connection with understanding quantum semantics of quantum systems at all.
It's really understanding vector space.
Exactly. So that's why he didn't get this. So the importance of the structure that he's picked up on here.
So another piece of structure, because in these categories we define, you've got loads of structures sitting which people actually have been axiomatized just recently and discovered. And like one of the things is for example the trace monoidal category, which is due to Joel Street and Verity. And this was like to axiomatize the notion of trace, which is important, for example, in computer science for iterative behavior. And that's how it looks in our case. So I can define something like that. Loop on an input and an output. In the Hilbert space case, this would be exactly giving you trace. Like trace of a density matrix which you use to normalize, or the trace you take from a... For example, trace is very important in quantum mechanics. Very important. So, and how do you read? You take the sum of the diagonal elements, yeah? This is the same thing as taking the sum of the diagonal elements, it turns out. So in pictures, taking the sum of diagonal elements is this thing. But this of course clearly shows you, like, it's a nice result that if you make the sum of the diagonal elements, it doesn't matter on which basis you express your matrix. It's a nice result. Well, here it's obvious that it doesn't depend on the base because there's no base. But it's the same thing. It's the same thing. So you've got trace.
And of course, I mean, if you do that, you have to sort of prove that in your vector, that if your vector space of vectors is an example of this category that what you write.
I did it here. I proved it here.
That these are actually independent of the base also.
Which?
That this thing over there is independent of the base. Which you write down over there. I mean, you have to do some work somewhere.
Well, it's obvious. I proved it, and I didn't specify which base I used. So it's true in any base.
And you can do it directly without the coordinate route.
And then
Trace and determinant can be written down or defined
yes.
in a coordinate field.
Yeah,
yes, you can. So, and like when I calculate here, I didn't specify my choice of base. I just took any base. So it's true always. And indeed, you can, of course, you can express trace without reference to base. Although, this is one way to do it actually. Like you wouldn't, so you can do it in terms of a Bell state and its adjoint if you want to. This would be like another way to write down trace without base, because Bell state I can define without choice of base. This is a delicate one. I can't define Bell state without choice of base. I should make this. But I only you can check this in a complex Hilbert space. This thing depends on the choice of base, provided I put this here. Now it doesn't depend on choice of base anymore.
Why?
What?
Why?
Oh, you can check this. Okay, this is something you have to check mathematically. Does this thing depend on choice of base? This does. If you do this, you can check this. It doesn't depend on choice of base
what
anymore.
the lower star means to conjugate? I'm confused.
Like the lower star really, like what is the conjugate space? Like I have to maybe, so we are actually not really working in the dual space. We're working in which is, so this thing